Have you ever just looked at the world around you and thought, there's got to be more to it? You know, some deeper layer that we're just not seeing. Well, today we're digging into the story of one individual who spent decades chasing that exact feeling, totally convinced that our entire understanding of physics is missing its most fundamental part. So let's rewind. The whole thing kicks off way back in 1986 with this one simple but incredibly powerful idea. Reality can't be a bunch of separate pieces. It has to be one unified whole. Now, that sounds pretty straightforward, right? But if you really take that to heart, it means some of the biggest, most established ideas in physics might be fundamentally incomplete. And that really gets us to the absolute core question that drove this entire quest. What if the physics we know and love, all the famous theories, are just describing the beautiful patterns we see, the symmetries, but not the actual machinery that makes it all tick? It's a wild thought. What if we've spent 100 years studying the shadow on the wall without ever truly understanding the object that's casting it? All right, so how in the world do you even begin to look for something like that, something that might not even exist? That brings us to the first chapter of this story, the search for that hidden machinery. Okay, so the goal here wasn't to just tear down everything we know. Not at all. It was about building a foundation underneath it. Think of it this way. Modern physics is incredible at explaining the rules of chess, how the knight moves, how the queen attacks. Those are the symmetries. But it says absolutely nothing about what the chess pieces themselves are made of. That's the machinery this quest was all about finding. The fundamental stuff that everything is built from. But here's the thing. If you're gonna look for a new foundation, you first have to be willing to question what's already built on top. And that meant taking a long, hard, skeptical look at some of the most sacred ideas in all of physics. You have to remember, back when our author was studying, these two pillars, the Standard Model and general relativity, they weren't just theories. They were the holy grail, the absolute pinnacle. So to even suggest they were incomplete, that they were missing their backing machinery, that wasn't just a new idea, it was practically heresy. And you can kind of see this way of thinking perfectly in this one little story. A professor stands up and claims that true mathematical analysis is purely abstract, no pictures needed, all while drawing symbols and numbers and graphs on the blackboard. And that sparked a thought. Hang on a second. Aren't those pictures? If even the most abstract ideas need some kind of physical representation, maybe all of science is resting on a physical structure we're not fully admitting is there. And make no mistake, this wasn't just some passing thought. It was a long, slow, patient burn over decades. It all starts with that core belief back in '86, which then leads to some early computer models in 2002, then a massive breakthrough in 2009, which inspired a new model for particles in 2013, all leading up, almost 35 years later, to a clear, cohesive vision for a totally new physics. This was a marathon for sure, not a sprint. So, after all those years of questioning, what new ideas actually came out of it? Well, to build a whole new reality, you have to invent entirely new tools. And that started with two really core concepts, C-space and continuities. One of the biggest aha moments came in 2009. Physics is built on this idea of a continuum, a smooth, unbroken line that you can divide forever. It's the bedrock of how we describe space itself. But what if that whole concept is wrong? Our author realized that the very tool we use to describe it, the number line, is actually made of discrete points. You can always find a gap. And that suggested a massive flaw in the very language we're using to talk about reality. So, how do you solve a problem that big? The answer was to invent a new mathematical object called the continuibit. And what's cool about it is that it's less of a perfect fix and more of an honest confession. It's like trying to draw a perfect circle using only square pixels. You can get really, really close, but you'll never capture that perfect smoothness. The continuibit is a tool designed to work with that limitation, basically admitting that our numbers can't perfectly map onto reality. And of course, if your whole description of space itself changes, you're going to need a new arena for physics to happen in. And that's space-time. It might seem like just a name change from Einstein's space-time, but that uppercase S and T are a huge deal. They're there to signal a massive shift in thinking. This is a framework where the universe isn't just a collection of separate points, but one single interconnected whole. Okay, this is all really cool, fascinating theory. But the real test, right? Does any of it actually connect to the real world? Let's take a look at how these ideas led to some very specific and testable predictions. So check this out. In 2015, before gravitational waves were officially detected, the author was asked if they existed. The response was incredibly bold. Yeah, absolutely. But, and this is the key part, they are not quantized. In physics, quantized basically means something is made of little, countable packets, like how light is made of photons. So predicting that gravitational waves are smooth and continuous, that was a direct result of the C-space model. It's a claim they still stand by today.
And this is where the theory gets even more provocative. So mainstream physics says galaxies spin way too fast for the amount of stuff we can see. To fix that, scientists came up with dark matter, some invisible stuff that adds extra gravity. But the C-space view offers a totally radical alternative. What if there is no dark matter? What if the real reason is just massive, large-scale gravitational waves sloshing through the universe, making the whole idea of dark matter totally unnecessary?
Now, why is this so important right now? Because just recently, in 2023, scientists confirmed a background hum of huge, long-wavelength gravitational waves all across the cosmos. For our author, this isn't just another cool discovery. It's the first hint of real-world data that seems to be closing in on what the C-space model predicted all those years ago. It's not proof, not yet, but it is a pretty tantalizing glimpse of potential vindication.
So, after this incredible, multi-decade journey of questioning, inventing, and predicting, where does it all land? Well, this last part is really a reflection on a life's work and what it means to build a whole new reality, even if you're the only one living in it.
You really get a sense of arrival here. The author feels that their personal mission is in fact complete, not because the world has embraced the theory, but because the conceptual puzzle itself is finally finished. The intellectual journey has reached its destination, even if the rest of the world hasn't quite caught up yet. Wow, that is such a powerful statement. It's this deep acknowledgement that this new reality might just stay a conjecture, an unproven idea. There's this quiet acceptance, this satisfaction in having built a complete, beautiful world of thought, and finding real comfort in that creation, whether anyone else validates it or not. And yet, the story doesn't just end there. It closes with this open door. It's a challenge, it's an invitation, and it's a humble admission, all rolled into one. It just leaves us to wonder, is this the secret blueprint for the next revolution in physics, just waiting for someone to prove it? Or is it a beautiful, intricate dead end? The personal quest might be over, but the final verdict, well, that's still out there, waiting for the future to decide.